Hi, welcome to Implicit Differentiation. This is the second part of 3 in the applications of derivatives, and we are looking at implicit derivatives because they're useful when we have y variables or when it's impossible or difficult to solve for y in our equations. And you might not remember some of these things, maybe from geometry or other math classes, but these are going to be your conic sections, which are like circles. We've got hyperbolas, which is like two parabolas away from, like facing away from each other, or we also have some stranger shapes, but also ellipses or ellipses. So we can get some interesting motion with circles and ellipses and other things like that. The one type of idea I'll be focusing on when trying to explain these relationships is going to be like bodies, celestial bodies, or these relationships you might see between planets and moons, satellites, and their systems. So we can think about that when we see these examples. But what sort of thing is described by multivariables? That's these circles, hyperbolas, ellipses. And you might notice that these are not necessarily functions, but it doesn't really matter. We can still find the change on any curve given that we have the relationship. So our implicit derivatives are going to be able to accomplish that. And this equation right here, you might recognize it, but this is a circle. This is the equation of a circle. And it looks like the Pythagorean theorem because it is, and that's how you make a circle. You just spin a triangle around an equidistant point from the center. So if we want to find the slope of any point on that curve, traditionally, if we look at 25 equals x squared plus y squared, we would have to isolate y. So we'd have to do something nasty and find some nasty algebra, that is 25 minus x squared, and find the derivative of this item, which would require a couple chain rules, but we'd have to do it twice because this is a plus or minus type of equation, which has two halves of the circle. So that minus half is the bottom and the plus half is the top. But we don't want to do, I just did all that algebra really fast. We don't want to have to isolate y really quickly or arduously each and every time we've got a circle or an ellipse or a different type of shape that we want to find the derivative of. We want to go straight into taking the derivative. Whereas before, when we were taking derivatives, it was great that we could rewrite some equations. Here, it's actually too cumbersome to take a derivative, to rewrite this into a nice form for us to take the derivative of. So it's too cumbersome. So with implicit derivatives, we can do the calculus before, or maybe not even doing any algebra at all. So our first example is going to look at 2xy equals 1. Already this looks strange. We got x and y on the same side of the equation. If we were going to do this normally, just to drive this point home, then we want to isolate y and take the derivative of what we have isolated. So I'm going to write this out, 2xy equals 1, and then isolate y. So y is going to equal, I need to move the 2x away, so y is going to equal 1 over 2x. Now, this is where we need to kind of go to back to basics a little bit, and that's when we take the derivative of something, we are applying a derivative operation on that item. So we are saying what's dx of y and dx of 1 over 2x. So you remember these ddx's, the d stands for delta. So what's the change in whatever over the change in x? So what's the change in 1 over 2x divided by the change in x? That's describing the slope. Now, we normally didn't show this operation happening to y, but I'm telling you now, that's what we were doing. We were finding the change in y over the change in x. And so we didn't necessarily write that left side, but we could do the right side quite easily after rewriting it some. So we would carry on and we'd go dy over dx. Oh, I'm sorry. We do need to rewrite this one based on what we know we can do. So we got 1 over 2x is 1/2 x to the negative 1. So we would go, what's the derivative of 1/2 times x to the negative 1? And you'd say dy dx, the derivative, is equal to negative 1/2 x to the negative 2. And then we'd be done. We'd be done with that. So that's pretty much a recap of how we started off with derivatives. We have this derivative operation that means finding the slope of the tangent line. And now we get to use a little bit more of that notation in implicit derivatives. So with this example, we are not going to isolate y. There's no algebra required, is what I'm saying. So 2xy is going to equal 1. So we're going to take the derivative of everything at once. So we're going to apply the derivative operation to everything. So if we go to the derivative of 2xy, then, and we're differentiating with respect to x, this is where things get a little shaky. We actually have two different items, two different things to take the derivative of, because we've got two separate variables. 3 if you want to count the coefficient, 2, but we can actually group that 2 with one of the variables. So we'll group that with 2x. So basically what I'm saying is we've got 2x times y, and that's like saying I've got one thing times another to take the derivative of one thing times another thing. That is the product rule. So if you can imagine those groups, if you can be all right with 2x is one group and y is one group, then now we just apply the product rule to those things. So the derivative of 2x with respect to x is 2. And then times the the thing that we multiplied by in the beginning, in the original function, so times y. And then we'll add that to the original function on the left, which is 2x, times the derivative of y. And we know what the derivative of y is. It's 2x, or sorry, it's it's dy dx. So here, if we didn't have that, and then equal to 0, because the derivative of 1 is 0. If we didn't have that, dy over dx, then we would be left without a way to actually find the derivative, because what we would have left over is just this 2y plus 2x, and that wouldn't actually give us, we need to have a dy dx isolated so that we know that what we have found is the derivative. Okay, so before we move on from here, let me actually isolate the dy dx. So dy over dx is going to require us to subtract 2y away and then divide by 2x, because we want to get everything that isn't dy dx away from dy dx. So we have negative 2y divided by 2x. Right, so we have found dy over dx, and that's great. It's represented as something with y and x. If we wanted it to be just represented with just the x variable, then we would have to go back, solve for y, if it was possible, and plug this 1 over 2x into y. And in that case, we could actually find the same type of equation, this negative 1/2 x to the negative 2 that we did before. So, I mean, I can show that so that you know that it's the same derivative. So I would do negative 2, 1 over 2x. But what in some of these cases down here, I'll show you how we're going to finish these, because they're going to be too complicated to solve for y. But you can see that this is actually going to be negative 2 over 2x times 1 over 2x. So that's going to be negative 2 over 4x squared, which is negative 1/2 x squared in your denominator. So they're the same derivative, but we're gonna leave the y variable in our solution, and I'll explain more about that as we do a couple more examples. So it's gonna be tricky at first, because you're gonna have to see x and y as two different groups that you need to take the derivative of. So let's go back to this circle, 25 equals x squared plus y squared, and determine the implicit derivative. Okay. We zoomed in too far. So we are going to just go straight into the derivative. Thankfully, I did choose a pretty difficult example. I know it looked pretty simple, but I did choose a pretty difficult example first. So this is not going to be one of those things where it's a polynomial, you can figure out what the derivative is without writing anything down. It's going to require that you write some things down, especially because you're using this notation and you're moving around y, for example. So we are going to determine the implicit derivative by applying the derivative operation d over dx to everything here. So d dx of 25, and if you want to be really specific, you can just sort of kind of apply the derivative operation to each term individually. And we can do that because we're adding these two terms, so we can take their derivative separately. So we see the derivative of 25 is 0. The derivative with respect to x of x squared is 2x. And now is where this is the new part of what implicit differentiation does. And that's we are going to take the derivative of y with respect to x. But we have this group on the outside of y called something squared. So that group on the outside of y is actually asking for the chain rule. And I know things seem really trivial right now, but once you get a hang of things, they'll be quite normal. So if this is, let's say that the y was instead like x plus 1 to the 5th. You wouldn't think twice when you're taking the derivative of this, hopefully, that you would use chain rule, because this is a binomial and you don't want to multiply that out. But here, y is tricky. It's not x. So we actually take that derivative separate, just like we take the derivative of the inside of a binomial separate from what the outside group is, which is, in the example I had, something to the 5th power. So this example of y to the 2nd power looks very simple, but it's going to require we take the derivative of that outside thing first. So we've got a 2, and then what was on the inside? Y, and then we reduce the power to the 1st power, so 2y. And then we multiply by the derivative of the inside, because that's what the chain rule says. So the derivative of y is dy over dx. There we go. So this is looking like the implicit derivative of a circle. And in order to round this one out, we want to solve for dy dx. So we want to get dy dx alone, because it's going to be more useful to us if we have the slope isolated. So dy dx is equal to, well, I just have to subtract 2x, so negative 2x, and then divide by 2y over 2y. Right, so coincidentally, this looks like a lot like our first answer over here with what was it? With example number 1, but it's y over x. So we're gonna get some weird things. So this means, if we remember that this is from a circle, this is the slope of a tangent line on a circle. Yeah. And if we were going to utilize this information, we look at what's the slope of the tangent line to this circle that we're talking about in example 2 at, well, I know a point on the circle, it's 1 radical 24. I should have a question mark there. What's the slope of the tangent line to the circle at 1 radical 24? And so if we wanted to figure that out, we can plug, we can substitute, plug in the x1, so 1, and the y, radical 24, into our derivative equation that we just found. And that way, we've got negative 2 over 2 radical 24. Or if we want to be a little bit more formal, we could rationalize that, and we could have negative 1 radical 24 over 24. So we have this negative slope on our circle. Now, this is gonna be practical for motion, and like I was saying, we could look at maybe some celestial bodies and try and make sense of these graphs here. And don't worry about example 3 at the moment, but our graph from the circle in example 2 is right here. So we would have a tangent line slope that we just found going through that green point, because that green point is 1 radical 24. So we just found the slope of the tangent line, which is negative 1 radical 24 over 24, which is represented here. And if we're imagining this, then it could be just the slope, the trajectory at any instant of like the moon orbiting the Earth, if the Earth is in the middle here. Right. And before we move on to example 3, I know this is quite a lot to learn, almost like a new mechanic with derivatives. So what I'm going to do is I'm going to speed up my work here for example 3, and you can pause along the way, or you can pause at the end when I show you the entire procedure I have. But this is number 4 on your practice, which you'll have attached to this. And yeah, I'll see you on the other side. All right, so this is the answer we got after taking the implicit derivative, which you should be all right with doing. It wasn't that much different than the second example. However, now we do have a little bit of a trickier end to this problem. We want dy dx alone, so we need to get dy dx's together on one side of the equation and factor. So there is a little bit of algebra at the end for this one. So what I'm going to do is I'll have my negative 4y, and I like to put parentheses with my dy dx's so that they look like they're grouped together nicer. Minus 4 dy dx equals 6x squared. And then what I'm going to do is I'll factor away a dy dx from everything on this left side of the equation. So what I'm left with after factoring that away is negative 4y minus 4, and that's going to equal 6x squared. So that my dy dx is going to equal 6x squared over negative 4y minus 4. Now I'm going to leave it there. I know it can be simplified if you divide 2 out of it, but that is the final answer for this problem. And it looks like a beast, but really you're taking it, the hardest part is going to be making sure you have done the chain rule right on these y squared, and you'll definitely get a pattern down for those type of things. Over here, my y, the derivative of that became dy dx, and yeah, there's the solution there, and I'll see you all in class. Bye.